So now that we have gone through our more broad assessment of the potential locations of ponds in the landscape, we can now turn to the places where we've identified as good pond sites and start to do more targeted observation and evaluation. And the place that I start is looking at the vegetation within the future footprint of the pond and the work site. You know, it's good to know what all the species are, both plant and animal, that would be impacted by earthworks in that area, and have a sense of if you're going to be impacting any sensitive species and potentially making a plan for also transplanting plants that could be used somewhere else in the environment or moved to a different area of the site. A stage of equipment mobilization, potentially even prior to mobilizing large equipment for pond construction, is to have a machine that can dig a nice and deep test pit. So the test pit is very important because it helps you evaluate what type of soil conditions you have for pond construction. The day that you do the test pit is a day to both do field analysis of your soil and also collect soil if you wanted to send it off to lab to have further samples. It's also possible, and sometimes a very good choice, especially for larger ponds, to have a geotechnical analysis that's done by a professional, and they may even put down a series of boreholes. So there's really a scale of decision making around how much technical analysis you do. But if you're building ponds that need to be engineered, especially, and there's often with water resources departments, there's requirements at a certain scale at which the ponds need to be engineered, a full professional geotechnical analysis may be called for. When you dig the test pit, you'll be looking for a few things. You'll be looking at essentially proofing the data that you've already collected about your soil types from the NRCS or other soil resources. And so you'll be looking at the soil profile. You want to see what the conditions are of the different soil horizons. And though this really varies, you'll see that there's stratified layers within the horizons. And the ideal situation is that a soil horizon gives way as it moves down to a less porous soil. So that you would move from a soil that has water and percolation moving through it to a soil that is less porous and has water coursing over the top. And you may even see, after you've dug your test slice, that water is cascading down the side of that lower soil horizon. That would be a soil with higher clay content generally. And if you get into the subsoil and find that you have deeper layers of heavy clay, this is the material that you're going to be using to build the core elements of your pond and using to seal the pond. You want to dig a bit deeper than the planned pond depth in order to see what the entire layer of soil looks like below the pond. It's possible that a really good layer of clay could give way to fractured bedrock or cobbles from a creek bed at a deeper horizon. And so you really want to know the entire depth of your pond. Another possibility is that you find that you have soil that doesn't really suit a condition that leads to a natural seal. So you might have just a very sandy and porous soil all the way down. At this point, you'll be needing to evaluate whether or not you want to bring in material to seal the pond, or if there's another better, more effective approach to your project. The other thing that we are really wanting to look for is the depth to bedrock. In a lot of cases, the soil depth may be just a matter of feet before it gives way to fractured bedrock and then actual bedrock. And if that's the case, that's essentially going to limit the depth of your pond. So these are some really important initial notes to make. So in addition to this work of looking at the cross sections of the soil, we also want to evaluate the structure of the soils. And so we can utilize a number of different field tests to look at that. We can carry out an analysis of the different soil profiles. And from each profile, we can collect clay and do a texture by feel analysis. And that's one way of determining whether or not there's enough clay to really adequately hold water. We can also look at the relative percentage of sand, silt, and clay by taking samples from each of our soil horizons and doing a jar test. Another field test is to look at water percolation by putting a nice gentle slope into your test pit, which is also really important as an aside to protect wildlife and critters and humans from falling into the pit and not being able to get out. You can use a nice slope to put in test holes for soil percolation. And so we evaluate the rate of percolation to get another read on the soil's ability to hold water. We can also combine lab analysis with like the Emerson test and Atterberg limits to look at the way that clay reacts with water and expansion and contraction, plasticity. There's a lot of things that we can look to do this soil suitability analysis. One thing to consider for soil test pits is how many test pits you want to put in for a given pond. You probably want to put in a few because you're wanting to look at the entire basin. A few test pits at the dam site and a few back from the dam could be a good decision. You get your preliminary test back, and hopefully these tests really show that you are good to go for construction. Some of the constraints may also lead to further decisions around whether or not, for instance, large stored water is the best choice, or maybe you're going for a lot of just infiltration and bioswales and a different agroecology altogether. Or maybe you do need that stored water, so you're looking to bentonite clays or pond liners or something like that to really adequately hold the water. Once we know where our pond site is, the next step is to generate cross-sectional and overhead view diagrams of the pond. We can look at how much soil we can expect to move. We can look at what is the total area that's going to be impacted, how many trees need to be removed, etc. We can start to perceive what some of the impacts will be on side slopes and things like that as we excavate to make sure that we're maintaining the proper inside slopes. A cross-sectional diagram would show the inside slope of the dam, the outside slope of the dam, the width of the crest of the dam. It would show the back slopes of the dam and what those look like. It would also illustrate whether or not there's going to be internal terracing in order to do aquaculture and create different microclimates within the pond, and the depth. Now that cross-sectional diagram can also illustrate the location of the clay that actually maintains a permanent seal on the dam and the bottom of the pond. When we look at a cross-section, we can see that there's really 3 ways to build the dam as far as the content of the soil type. The first and the best way to build the dam is to put in a key. Now, a key is really critical for assuring that the water doesn't move through the dam. As water moves through a dam, it sort of drops as it goes. It would slowly wick through a dam, and if it hits a interior clay core, that is going to create a really well-built key core, will prevent the water from moving all the way through the dam, which then would prevent channeling and piping through the dam, that could lead to erosion and the blowout of the dam. It'll also just functionally keep water in the pond. A keyed dam is built with an internal key that goes up and above the ultimate height of the water. The topsoil and the less clayey material creates a skin on the top and the sidewalls. Now the dam itself also has some very critical components. The best type of dam one can build is a dam that has a central clay key. It gets built into a trench that crosses all the way across the length of the dam from both sides of the valley. And this is where you put the best, heaviest clay material, and you'll build that key up, starting from that trench all the way up to your desired water level. So the key is a critical element. If you don't have enough clay to build up a key, there is a second type of dam that can be built, and this is called a diaphragm dam. So this would be a situation where you essentially continue that clay blanket that's on the bottom of the cutoff excavation, and you work it all the way up the side of your dam. So you have an interior liner of clay that serves the purpose of preventing excessive water movement, at least through the dam. A third type of dam, which really is not recommended and that I really try not to build. In theory, if you have enough clay, you can just build what's called a homogeneous dam, which is a dam completely constructed of clay that just the wall itself is keyed into that trench at the bottom center of the dam. Still, it's always a good idea to really maximize the heaviest concentration of clay at the center of that dam to create that permanent seal. Starting from the bottom of the pond, it's very important to keep in mind that the bottom of the pond needs to be excavated all the way down to the impermeable layer. So if you have clay, the bottom of the excavation, and this is called the cutoff excavation, should be at that impermeable layer and connect with the dam. The dam then sits on top of a keyed in depression that goes even deeper into that impermeable layer. Now, if in your excavation you dig down and you hit fractured bedrock or some more porous layer at the bottom of the pond, a workaround for that is to lay down a blanket of clay that sits atop that layer, which ultimately would be the impermeable bottom of the pond. And it's very important to check this into the dam so that there's a complete seal along the entirety of the bottom of the pond. So if we now look at the pond from a bird's eye view, we can talk about some other key elements. One is the spillway. So the spillway is the way that we pass live flow around the dam. Every pond needs a spillway. The spillway needs to be designed to handle the flow or the discharge of the watershed through itself, and the ideal spillway is built to handle 3 times the total storm flow coming off of the pond. The first key to a spillway is that it is not built over or even within any of the loose soil that is left from the dam construction, but instead is built around the dam into the native soil on one side or the other of the valley. The spillway is for moving flow out and around the pond when the pond is full. The height of the bottom of your spillway is going to determine your ultimate water height in your pond. The ideal scenario is that from the top of your dam to your water height, you have typically 3 feet for large ponds, and for small ponds, at least 1.5 to 2 feet of freeboard. So freeboard is the term for the distance from the ultimate water height of your pond to the dam top. Now this assures that under no condition will water go over the top of your dam and find a new point to flow over and erode the dam. So the spillway sets the height of your pond water and therefore your freeboard. Technically, freeboard represents the vertical distance between the top of your spillway and the top of your dam. One way to determine the height of your freeboard is to look at the horizontal distance from your dam to the backside of your pond, and that's called the fetch. The longer the fetch, the more potential you have for wave action, which could lead to, the water overtopping the dam. One way to minimize fetch is to build an island and have that island intervene in the wave action that could be affecting your dam. Another element to consider is your inlet. On steeper ground, as you construct your pond, you can create steeper banks behind than the natural landscape condition, and in those situations you may have water seeping down or pouring down those banks. It can be really important, one, to make sure that the backside of your pond is built to accommodate some saturation in water and won't slump after the excavation. At the inlet itself, where the water courses through, you might see an erosion gully form and a head cut, and this could be one place where that water causes erosion and leads to slumpage and accumulation of sediment in the bottom of your pond. So right away, it can be a good idea to put live stakes or woven bundles of willow and red stem dogwood or any other type of woody riparian plants that you have on hand to anchor that space. In the near term, those live stakes may not provide very adequate erosion control. So one way to go is to stake a bunch of rows on contour and then backfill with straw and other plant material and woven brush mattresses that can get embedded into the dirt there and will ultimately sprout and grow so that they create a permanent cover and erosion control. And we can see in this pond as an example of that, where we planted in willow and dogwood and wapato on the terrace there to mitigate that erosion at the inlet. Another element to consider in the process of construction of the spillway is the trickle tube. So a trickle tube is classically used to minimize small seasonal flow over the spillway. So this cuts down on just the long-term erosion of a small trickle as it moves over the spillway. It basically skims surplus water and moves it via a pipe around the dam and puts it back into the channel. The trickle tube can be installed at the same time as the spillway is built in connection to the dam. And it usually wants to just run right through the edge of the spillway and out. You would basically be wanting to have a tube that's big enough to accommodate your seasonal flow. And the spillway then can be thought of as a way to handle surplus flow and storm surge, as well as if you have larger flow during certain times of the year, that would be more likely the route for that surplus water. The trickle tube can also be used as a way to skim a portion of the surplus and route it out to another storage. So a trickle tube also can be a way to carry water via a pipeline to another pond. So in this way, if we're actually diverting water out of a drainage, we can be sure that the bulk of the water during the rainy season continues through the spillway and through its natural riparian ecosystem. But the surplus water, or a portion of that surplus, can flow to the trickle tube and be carried out and beyond the valley. It can be carried out to the ridge, or it could even be allocated to go to a valley pond the next ridge over. If I feel like there is an intact riparian ecosystem with the integrity of a natural waterway, I don't like to take water out of a valley and permanently divert it into a next valley over. It's important to consider as you move water from valley to valley, if you're doing watershed scale earthworks, that you might not want to steal too much water out of any given valley. So a trickle tube is a way to take just a small amount. You can also have an overflow swale that's separate from your spillway to do a similar function if you have the type of soil and the surplus water to do that. Generally speaking, I think it's very important to consider the idea of moving water from valley out to the ridge and back to the valley before just moving it from one valley to another. The final element to consider is the outlet pipe. You'll want an outlet pipe if you're using this water for any irrigation use. It's important for aquaculture and fish culture, and it is also important for draining and servicing the pond. Oftentimes, people will build the outlet pipe right through the center of the dam. In that case, the most important thing is that this pipe is made so that it is long-lasting material. I would recommend just using a good PVC. Very importantly, this pipe should have cutoff collars installed along its length. And what these do is they prevent flow from moving along the pipe and eroding along the pipe and creating a tunnel through the dam. That would be the proper and long-term well-being of the cutoff collars is really important. People will pour concrete forms around the pipe as is laid along through the center of the dam. You can also use rubber collars that slide along the pipe. And if it's a steel pipe, also weld cutoff collars. The trickle tube usually just has a single cutoff collar. You can have more than that, but the trickle tube also needs to be outfitted with a cutoff collar. Another option for the outlet pipe is to have the pipe just go right over the top of the dam and have a siphon. That's a sort of easier and safer way to go, but it takes a little bit more maintenance. You can run your pipe up and over into a screened outtake in the pond, have it go up and over the dam and back down, and there's certain conditions you need to be able to create an adequate siphon with enough drop to really get that water moving well and into the pipeline. The siphon can be primed simply by filling a 5-gallon bucket and pouring it into a T at the top of the pipe from the dam. So that's a nice sort of low-tech way of priming the pipe. Valves for controlling the flow of water through the outlet are important, and it's important to use a gate valve type, which would be one that you can screw down slowly and open slowly in order to moderate the flow and not have it come out in a single burst. The valves can go on the inside, within the pond, or outside, and it's really a matter of preference, but most people put the valve on the outside of the dam because it's more accessible and it's not exposed to water. The outside valve can take more pressure, so it can end up being more leaky, but the inside valve, being exposed to water, can degrade quicker. It's a little bit more challenging to maintain and to service. So my process with construction is to start by clearing the topsoil of all organic material and debris and getting down to what feels like an adequate workable material for the main frame construction of the pond. This means that we're removing at least the organic and maybe the A horizon of soils. That typically just gets pushed downhill of the dam, and we'll use that later to skin the entire outside of the pond. The area that gets focused on next is the cutoff excavation zone of the dam itself. So we're excavating down to the point where we have the adequate type of non-porous and strong material to anchor the pond dam into. So we'll excavate that material down until we're at that satisfactory depth, and also relative to the ultimate depth of the pond itself. Then at the bottom of that excavation, we build a little key for us to start piling the best clay, the best heavy, strong material into the core of the dam, and we'll build that up. As we make that excavation, we want to be careful, first of all, not to scratch and break up the dirt, the clay material at the bottom point where the dam will anchor into, because that can create a weakness point. But we can go to the outside edges of the dam where it's going to key into the side of the valley and create notches with the bucket, the tooths of the excavator, for it to get packed and keyed into on both sides. Once we've done that, we can start to build up the key. Now, if this surface has become really dry, it might be necessary to wet it down a little bit to get that good connection. And we'll start to add layers into that core. And as we build it up, we want to build this core up as we go, so that that perfectly thick clay core goes all the way up to above the height of the ultimate water level. Sort of simultaneous to this, we're stealing material from other subsurface soil horizons adequate for dam construction and piling that on both outside edges of the key. And as we go up every couple inches, we want to make sure that we get adequate compression on the top of this dam wall to make sure that it gets really compacted and stabilized. Usually it's really useful to use a sheep's foot roller to do that compaction, and there's calculations that can be made by volume on and by the type of clay that we're working with to determine, you know, how much weight and how many passes of a roller we need to utilize in order to get that good stability. We can also track roll with the machines we're working with, but bulldozer, excavator. On small ponds, I have actually used a rototiller to till and create a compacted layer, and doing that as we go all the way across. The rototiller actually creates a good compacted layer below it in the clay soil. So compaction is really important. As we build the dam up, we get to a point where we can be looking at the connection to our spillway. And so once we have built up to that ultimate dam height, we can cut that spillway into the side of the dam, into the native soil of the side slope of the valley. And that then gets built with the same 2-to-1 slopes on the outside and a flat bottom, and designed so that it can pass that water well around the dam. You never want to build a spillway over the top of a constructed dam, as it will erode the dam. Once we feel that we've adequately gotten the main frame of our dam, we can work on smoothing the top, and we can go back and do final shaping on slope on the inside and outside of the dam. As we build up and remove material from the excavated section of the pond, we want to be also sure that we're creating a non-erosive slope on the backside of the pond. And so we'll be looking to have a 1-foot rise by 3-foot run, typically going all the way around all sides of our pond. Once we have the dam shaped and the sidewalls of the pond constructed, we want to come right in with seed. Bunchgrass seed is a very good choice for the dam surfaces. You can also stamp in seed from native juncus and sedges. But the most important thing is to remember not to put any woody plants on the dam itself. So you never want to have trees or even any really woody plants growing on the outside or inside of your dam. If they are, they can put their roots through to reach the water, and that'll create a channel for water to flow through and compromise the dam. It's also important not to have large trees in a location where, if they were to be thrown over and uproot, that they could break your dam substantially. Your spillway also every year should be evaluated and cleared if there's any accumulated sediment or certainly, brush material in it. Now that we have our pond built, all we have to do is sit and watch the water level rise until we're ready to jump in and get cool and revel in the fact that we can be supporting biodiversity and wildlife habitat, water security for fire control, water for gardens, water for orchards, a place for the kids to grow up learning how to swim, and just a wonderful spot for friends and community to gather. So I wish you the best in your journey with water and pond construction.